All right, guys. Hi, everybody. So I'm going to be doing a video that kind of covers the introduction to the motivation for integration and the techniques so that I can close the gap between maybe when people's last semesters or quarters ended and this one began, and also to remind some people that didn't do any math over the summer where some of these ideas come from. So this is kind of an ad hoc video, so you're not getting the full studio presentation that you'd get out of the normal lecture videos, but I hope this is clarifying. So the big question in the idea of integration is to calculate the area under a curve. And I want to talk about where that idea even comes from originally. So remember from Calculus 1, you had the idea that if you had a graph, and that graph described, say, displacement, and you wanted to know, so by displacement I mean you have an object moving around, so this is the location of a moving object. Then if you wanted to know where or how fast the object was going at a particular location, you could use the derivative, right? So the whole point of differentiation is that if you tell me where an object is at a particular time, and you look at the slope of the tangent line at the displacement curve there, that the slope of this line, so the slope of the tangent line, is equal to the instantaneous speed. Okay, so the idea is if you had something like position and you take a derivative, then you end up with speed. And you also learned that if you take speed and you take a derivative, that you end up with acceleration. So remember that this was all motivated originally by physics. So the mathematicians who studied calculus at the beginning of the subject were interested in questions in physics. That's what calculus was invented to do. So the big question is, what process is there for going the other direction? So if I want to go this way, suppose that I knew acceleration and I wanted speed, how do I do that? How can I go this way? Okay. If I had speed and I want to know position, how can I go that way? So integration is the process that undoes differentiation in some sense. Okay, so it's the inverse operation. It is the answer to the question, how do you go backwards? So I'm going to try to motivate where it comes from originally. So here's the question. How do we go from velocity to displacement? You can think by displacement how far you've moved away from where you started, right? So that's what displacement means. How far from the starting point. So if I had a constant velocity, this question would be easy. So suppose you have some object, and that for 1 hour, the object travels 60 miles per hour. So this is going to be a velocity graph up here. And let's suppose this is 60 miles right here. So this is in miles per hour. This is measured in hours. And it turns out to be the case that if your velocity is constant, so if your velocity never moves, then the area of this rectangle, so the area tells you how far you went. Even from the standpoint of dimensions, this makes sense, because down here we've got time measured in hours. So This dimension of the rectangle is measured in hours. This dimension of the rectangle is measured in miles per hour. So if you multiply length times width, the unit when I take hours and I multiply by miles per hour is equal to miles. Okay, so if the velocity is constant, I can use area to figure out how far I've gone. So of course, in most situations, the velocity isn't constant, but this relationship still holds. The idea that the area underneath a chunk of velocity tells you how far you went is still a valid idea. So now imagine that we have a velocity curve that looks like this. So this is the t-axis, and this is the v-axis. And let's suppose this time that my velocity curve looks like this. I'm going kind of slow, and then I speed up really quickly, but then my speed tapers off until it's constant. So whatever those numbers are. Maybe this is 30 miles an hour, and this is 60 miles an hour. The idea, or the answer to the question, how far did I go, still comes from the same thing, right? The same idea that the area contained underneath the velocity curve is going to tell us what our displacement was. Because after all, we're still multiplying miles per hour by hours. The problem is that this region isn't rectangular anymore, okay? So the first idea you might have is, well, maybe what I could do is I could pretend that it was rectangles. So let's just pretend that I'm going to pick the left end point. I'm going to make two rectangles inside here, and I'm going to pick the left endpoint of each of these rectangles on the curve. And I'm going to estimate the area underneath the blue part with this red area. So the red area is an estimate of the displacement. Okay? Now I could get a better approximation by making smaller rectangles. And the more rectangles I have, the better approximation I'm going to get. So essentially what I'm doing is I'm pretending that on this little chunk right here, that velocity is constant. And on this chunk right here, I'm pretending that velocity is constant, because then I can use the same idea that I had on the previous slide. That is, if I have constant velocity, I could just multiply by the time I traveled, and that tells me how far I went. So I'm changing a problem that is not a constant velocity problem into one that is a constant velocity problem. Okay, so one big question is there a way that I can make this more rigorous? Okay. How to make this rigorous. So the idea about being mathematically rigorous is that it's systematic and it applies to more situations than just one. Okay. So we can actually write this down, an area problem like this, in a specific example. So let's suppose that this was our velocity curve right here. So v and t. And this velocity curve is equal to your velocity at time t is equal to t squared. Okay, so if you tell me what time I'm moving, then I can tell you how fast I was going at that time. And I want to know how far I went between t equals 0 and t is equal to 1. So in the hour between 0 and 1, how far did the object that has this velocity curve get from the origin? And the answer is, like before, I mean, the easy answer is, oh, it's just the area under the curve. But the velocity is not constant, so we have to pretend that it's constant. And that means that we're going to approximate with rectangles. So the name for the sort of approximation we're going to do is called a Riemann sum. That's the fancy name. So all that a Riemann sum is literally approximation of area by rectangles. So let's actually see if we can write down an expression that makes this make sense. Well, how about I'm not going to do 2 rectangles or 3 rectangles, but I think about cutting this region up into n rectangles. So I start cutting along this axis. And let's suppose that I make n rectangles. How wide is each rectangle? So you can just think here, well, you've got these rectangles that look like this. I'm going to choose these rectangles to have height at the left endpoint. So what that means is I look at a little piece down here and I travel up the left side, and wherever I hit the graph, that is where I put my rectangle. On the next interval, I put my little interval down here, I travel up the left side, and wherever that hits the graph, that's my next rectangle. I travel up the graph, wherever that hits, that's my next rectangle. I travel up wherever that hits, it's my next rectangle, and so on. So this is called a left endpoint approximation. And what we're going to try to do is we're going to try to write a formula down for the height of these rectangles, and then we're going to add it up. Okay, so how are we going to make this rigorous? Let's take a look and see what we've got. So I know that I've got, say, a curve that looks like this. Same curve from last time. So let's suppose that this is v is equal to t squared. And what I'm going to do is I'm going to cut the interval down here up into n equal pieces. And that means that I want to look at where these points are. Well, the first point is at 0. This is supposed to be also the t-axis. And the next one, well, if I jump over, and I've cut this into n equal pieces, the next point should be at 1 over n. And the next point is at 2 over n. And the next point is at 3 over n. And so on until I get to n minus 1 over n. And then finally, I get to n over n, which is 1, which is the end point. So I'm going to build some rectangles out of this in the same way that I described. So what I want to do is, each rectangle, I'm going to evaluate the function at the left endpoint, and then I'm going to use that as the height of the rectangle. So you can imagine what I'm doing here. So imagine there's a ghost function up here. So this ghost function is v is equal to t squared. To make my rectangles, what I do is I say, okay, well, the left endpoint here is at height 0. So the area of that rectangle is 0. So the area of that rectangle is 0 times 1 over n. What's the height of the next rectangle? Well, the next rectangle touches the curve right here. Then its height is 1 over n squared. Right? Because the graph is v is equal to t squared. So if your t value is 1 over n and you square it, then your height is 1 over n squared. The next rectangle, oh, I suppose I should finish here. The area of that rectangle is 1 over n squared times 1 over n. Height times width, because the width is always 1 over n, right? So this width right here is still 1 over n. What's the area of the next rectangle? Well, it's 1 over n in this dimension, and its height, that is the distance from here to here, is just going to be 2 over n squared. The height of the next rectangle will be 3 over n squared. And so its area, the area of this one, is going to be 3 over n squared times 1 over n. And the area of that rectangle will be 2 over n squared times 1 over n. And if you want a sum that approximates the area underneath this entire shape with these left endpoint rectangles that I've been drawing, then the area is going to be about equal to 0 times 1 over n plus 1 over n squared times 1 over n plus 2 over n squared times 1 over n plus 3 over n squared times 1 over n. And you just keep going until you get to n minus 1 over n squared times 1 over n. The reason that you stop here is because the last rectangle has a height dictated by that point right there. Okay, so each one of these is the area of a rectangle. this is the area of that rectangle, and this is the area of that rectangle, and this is the area of that rectangle, and so on. And if you add up all the rectangles, you get an approximation for the area under the curve. Okay? So this thing that we've written here, this is what we mean when we say Riemann sum. So this is an example of a Riemann sum. These things are easier to work with in sigma notation. So let's actually write down our expression. We know that the area was of underneath our curve was about equal to 0 times 1 over n plus 1 over n squared 1 over n plus 2 over n squared 1 over n up to n minus 1 over n squared 1 over n. Notice each one of those terms has a 1 over n in it, and so it's going to factor out. And then what you're left with is 0 plus 1 over n squared plus 2 squared over n squared plus 3 squared over n squared up to n minus 1 over n squared. And each one of those has a 1 over n squared inside of it, so you could turn this into 1 over n to the third times 0 plus 1 squared plus 2 squared plus 3 squared up to n minus 1 squared. Or in sigma notation, the sum from I equals 0 to n minus 1 of I squared. Now that's almost a formula that we know, because one of the things that you learn or that you're given when you get this section is some standard formulas for computing sums that look like this. So you learn that the sum from I is equal to 1 to n of a number 1 is just equal to n. That's easy. N ones just adds up to n. That the sum from I is equal to 1 to n of the first n integers is equal to n times n plus 1 over 2. That's a fun formula to work out. And then relevant to us, that the sum from I is equal to 1 to n of I squared is equal to n times n plus 1 times 2n plus 1 over 6. And that's a formula that we're going to be able to use in this context. So you should notice that the starting index doesn't match correctly, right? Because we started with 0, and there are these 1s in here. The thing is, the 0 doesn't count because it's just a 0, so you can throw that away. So you might as well replace this with 1 over n to the third. The sum from I is equal to 1 to n minus 1 of I squared. Now I can apply the formula. The formula says whatever this number is up here gets plugged in for all these n's on this side over here. So what I'm going to do is I'm going to move away from this concrete sum, or this like sort of abstract sum. I'm going to turn it into a concrete formula. So applying the formula, I'm sorry, this formula right here, this turns into 1 over n to the third. And then what do we get out of the formula? Well, everywhere I see an n in the formula, I've got to put an n minus 1. So I get n minus 1 times n times 2 times n minus 1 plus 1, all divided by 6. And that is just a concrete formula. So now what I've done is I've taken, so let's think for a second about what we actually did here. We took this graph where we were trying to approximate the area by rectangles, and then we wrote down a geometric expression for what the areas of those rectangles were, and then we've turned that into this algebraic formula right here. So the idea is, this is an expression that if you told me the number n, if you gave me n, I could tell you the area. Okay? But the idea is I don't want that, and that would be an approximation, because the number of rectangles that you tell me is going to determine how good my approximation actually is. So we can just algebraically simplify this real quick. So this is 1 over n to the third, and then there's a 6 here, and this turns into whatever it turns into, n minus 1 times n, and this is going to turn into a 2n minus 1. Okay, so the more rectangles you give me, the larger n gets, the more accurate this gets. So this is an approximation that's approximately equal to the area that we were studying originally. So whatever this is, if you tell me n, I could figure out what that area is approximately. So area is about equal to, the area that I get here is about equal to this guy. How do we get it exactly? Well, to get it exactly, let the number of rectangles n go to infinity. If the number of rectangles goes to infinity, then this approximation gets infinitely good. So what I could do is I could take a limit as n goes to infinity of the approximate area and that's going to be a limit as n goes to infinity of this formula. Well, you learned how to compute limits like this when you did calculus at the very beginning, right? Limits are the foundational idea of calculus. It turns out to be the case that this is a comparison of polynomials. So on the top you have a cubic polynomial whose lead term is 2n to the third. And on the bottom term you have a cubic polynomial whose lead term is 6n to the third. And when you have a rational expression like this and a limit going to infinity, you can say that that limit is equal to the quotient of the lead terms. And so what you get out is 1/3. So this right here, this is the exact answer to the area underneath the curve. And we have a special symbol for this. Because we added up rectangles, so I was looking for the area of this region right here, and the way I did it was with a bunch of rectangles, and then I added rectangles. So the area of this region is about equal to a sum of rectangles. Well, sum is a word that starts with S. So what we do is we say, oh, well, I'm going to take the sum from t is equal to a to t is equal to b of v is equal to t squared. That was the height, right? Times delta t. So these things are just the areas. This is the area of a rectangle. So this thing right here just represents dt, things we're thinking of infinitesimally small instead of 1/n small. So this thing is called a definite integral. This is a definite integral. And what we showed is that the area between t equals 0 and t equals 1 of the graph t squared, of these rectangles that we get out of with a height t squared and a width dt, is equal to 1/3. So that's what we showed. And we showed that using nothing more than geometry and limits. We did this with geometry and limits. Okay, so that's kind of where definite integrals come from. You take a curve that you're trying to compute the area underneath. The reason that you're trying to compute the area, and you should imagine, is that you've got some sort of velocity curve, and if you could chop it up into rectangles and compute the area, you could figure out displacement. So this is a technique for taking a velocity curve and getting a position out of it. So this undoes differentiation. So what we've done right now is we started with v of t, which was a velocity, and then we computed its area, and what we got out the other side was a position or a displacement. Okay, so this is the opposite process of differentiation, right? We've undone differentiation. Differentiation goes this way. Differentiation would say, well, you started with the position, tell me what the velocity is, but we started with velocity and we figured out position. So derivatives go this way. Now the problem is that the technique that we used is really nitpicky and it takes a ton of work. So our next big question is, can we make this systematic? To do it, we're going to need two things. First, we need to verify that what we just did is the opposite process of differentiation. And the second thing we need is a way to actually do calculation without having to use limits all the time. Because I don't want to have to do this every time I'm trying to find the area underneath a curve. Although I'll point out, almost every modern computer does integration this way. So when you're doing numerical integration in an engineering or scientific context, it's not computing some function and plugging in numbers. It's doing it exactly the way we wrote it down right here, where it approximates by cutting things into rectangles and then approximating the rectangles. Okay. So the next video is going to talk about how we take this idea of a definite integral that represents an area and actually use techniques that we learned in differentiation to work on it. Okay. So next video will follow.